Good morning. Welcome to the channel. I'm continuing with the homogeneous higher order differential equation with the constant coefficients, where you can actually solve it, subject to, of course, the characteristic polynomial getting split. So that's the only handicap that you have, which cannot be assured. Yeah, so the expression L is given by the nth derivative of x plus sigma I equal to 1 to n ai dn minus ix divided by dt n minus I, where ai's are all assumed to be constants, that is real numbers. The equation is Lx equal to 0, which is homogeneous with p lambda equal to lambda to the power n plus sigma I equal to 1 to n ai lambda to the power n minus I. P is the characteristic polynomial of L. Then, of course, that you can get because what you do is higher order equations you transform into the system, and the first order system of n simultaneous equations you know how to find out. So it is of the form dx by dt equal to ax. Now look at the characteristic polynomial of A. That is precisely this p lambda. So P is the characteristic polynomial of L. Then we use the notation d equal to this we have used earlier, d equal to d by dt. The equation is P dx equal to 0. Lambda 1, lambda 2, etc. lambda k are distinct roots of P over C. I think I have put it in the lecture 30. All these details are there. Then P lambda is this, only for continuity I am just doing this. P lambda equal to lambda minus lambda 1 to the power m1 etc. lambda minus lambda k to the power mk, where m1 plus m2 plus etc. mk equal to n. Now here we are splitting it over complex numbers, otherwise it may not split into linear factors. This is a problem, but it doesn't matter. You do it over C, and then once you have the complex solutions, you know how to get the real solutions which span the vector space of solutions. So that we will take care of, and one of the examples that I am going to do at the end of this talk will substantiate or tell you how we do this. So any solution of this is a solution of Lx equal to 0. That is obvious because, and here again we use the commutativity. These factors do commute. Therefore, you can bring it to the front, and d minus lambda I to the power mi can be brought here using commutativity, and if that factor d minus lambda I to the power mi of x is 0, then obviously Lx equal to 0. So that's very simple. And here commutativity is used. Now using the identity, so with this we have proved earlier, d minus lambda to the power m e to the power lambda t xt is e to the power lambda t d to the power m xt. I mean, it's a very useful identity, and we can show that, see, d minus lambda I to the power mi x, that is you write you bring it in between e to the power minus lambda t and lambda t, and then work e to the power lambda t and then use this identity, etc. Eventually you can show that this amounts to d to the power e to the power lambda t lambda I t d to the power mi xt equal to 0. So you can okay, d to the power d to the power mi, so I will just write it here. So it will be d to the power mi, sorry, d minus lambda I this you can write as e to the power minus t This is something that you can do. So the consequence is that okay, I'll just correct it. I mean, in fact, I have done it explicitly in the last lecture. So I'll just, nevertheless, we'll recall it. So you can prove this, that d to the power k xt, which is identically equal to 0, and now this is equal to, you can show that e to the power lambda t into d to the power m e to the power minus lambda t into xt. This you can show. And this equal to 0 then means this equal to 0, which implies that you have e to the power lambda t d to the power m of this equal to 0, and e to the power lambda t is not equal to 0. Therefore, this, so d minus lambda to the power m xt is identically equal to 0 implies you have d to the power m therefore you can write e to the power minus lambda t xt as a polynomial in T of degree at most m minus 1. Okay, so that's how it comes. So you have this result. So xt is of the form p mi minus 1 t e to the power lambda it for I equal to 1 to k, where we have taken pjt is the, I'll write here, so pjt is the polynomial of degree less than or equal to minus 1. So this is the, these are the details of this. Okay, and therefore now we introduce a set of functions. This is the block that we introduced, xij we define in this way. Then what the theorem says is that there are all solutions of the equation Lx equal to 0. This set of functions form a linearly independent set, and there are n elements in this, and you know that the solution space of Lx equal to 0 has dimension equal to the order of L, which is equal to n. Therefore, we have these functions linearly forming a fundamental system of solutions for the problem, so that every general solution can be written as a linear combination of xij's. This is the part, but that needs just one line or one statement, namely that these functions, these n functions xij t are linearly independent, and that's the That's what we have to prove here. So let me write down the proof. Now we can work on the proof of this theorem. So this is just a summary of the lecture 30, which had to be discontinued because of some technical problem that cropped up while recording it. So whatever portions were recorded, I have retained, and from there on I am continuing it, or from the statement of this theorem I am actually continuing it. So we prove this theorem now. Just write down the proof of this theorem. So let me write down the proof. So we want to show that so consider a linear combination whereCij's constants. So here, of course, what we have is that j running from 1 to mi and I running from 1 to k. Okay. Now we want to prove this. So let us see what it is. Now this sigma double summation Cij xij t is identically equal to sigma I equal to 1 to k pi t, sorry, e to the power, where PIT is a polynomial in G of degree mi minus 1. It's quite easy to find it out. Okay, because these are the definitions of, you can work with this. That's easy to verify. Then Px or P okay. being distinct, we shall prove that PIT is identically equal to 0. That's the first thing that we prove. Okay. So how do we prove this? Prove this by induction. Now you know that if a polynomial is identically 0, then you know that all the coefficients are 0. So it is enough to prove this. Once we prove this, then you see that the coefficients that appear in the polynomials are all Cij. All the Cij's are individually 0. That's what we prove in the theorem. Okay. Then how do we go about doing it? It's simple. Now we prove this by induction. This is true for k equal to 1. Because when k equal to 1, what you get is, suppose there is only one eigenvalue in it. So the form lambda minus say lambda I or some mu, lambda minus mu. So this is lambda minus lambda or mu to the power n. Okay. This is what happens when k equal to 1. This e to the power, what is it? You have p t e to the power mu t. This is what you get. And then you see that what one has, sorry, this one, yeah, where pt is a polynomial of degree n minus 1 less than or equal to n minus 1, and you see that this is e to the power mu t is not equal to 0, therefore this implies pt equal to 0. So that's very simple, right? So we shall now assume it is true for what is it? K equal to m minus 1. And then we show that it is also true for k equal to m. The usual induction argument. K equal to m minus 1. Then what do we have? That is sigma I equal to m minus 1 equal to j 0 implies but these are polynomials. Now we shall prove it. So for I running from 1 to m, so let this relation with lambda I not equal to lambda j if whenever I not equal to j. Okay. So what you do is you write this in the following form. Identically equal to 0. What you have done is by dividing by which is not equal to 0 for every t. Therefore, this is justified. Now from here we try to argue this. See, as such, this is a polynomial of a certain degree. Say, assume. So we shall assume that Pm are, say, then what happens? You take this relation, then differentiating, t, what you get is the following. Sigma I equal to 1 to m minus 1 if you differentiate this, this is what you end up with. Obtain pi differentiated, one is pi differentiated and it will be 1 degree less, and then multiplied by lambda I minus lambda m. Sorry, yeah, this is going to be something like this: qi t e to the power plus zero, where qi is equal to pi derivative t plus therefore you see that the qi degree of so the degree does not change of this polynomial, right? Now what we do is we differentiate it r times, okay? Or we shall differentiate it as many times as required to get rid of this term. Okay. Now after differentiating this relation with respect to t as many times as you required to get rid of that last term, Pm derivative of t. Sufficiently many times. Because we are assuming Pm is a polynomial of degree r, therefore we know exactly how many times you have to differentiate it. We have sigma I equal to 1 to m minus 1 RIT equal to 0, where degree of PIT. This is the important part. The degree remains the same. Now from which you know lambda I minus lambda m is not equal to 0. Hence we infer RIT is equal to 0, is identically equal to 0 for that is using the induction hypothesis. Okay, but still we have not got what exactly we want. What exactly we want is we want to conclude that all the PAs are 0. Okay, let us examine this problem. Now you can give a proof of this. Note that see, I am writing a pt e to the power lambda t derivative. This is equal to, what do you get if you differentiate it? Lambda into plus p derivative of t lambda t. Okay, and pt equal to 0. Then what about this? So what we want, so therefore if this is identically equal to 0, then pt is identically equal to 0, but you get a coefficient here, so we want to conclude that this is identically equal to 0. So is, okay, suppose, okay, what is this? Let pt be equal to t to the power some r m r plus say something like say p or say pr. Then what about this term? Let us work it out. Then lambda times pt plus p prime t equal to lambda times t to the power r, or let me write here p naught. PR plus, what is this p derivative? This is equal to p naught to the power minus 1. Okay, so this is what you get. This is this term. Okay. Now suppose this is 0. Can you conclude p is 0? Let us see what you get. If you have this equal to 0, then you are going to have p naught equal to what? P naught equal to 0, because that is the coefficient of r to the power pt t to the power r. Now this implies the coefficients of each of these terms are 0. P naught equal to 0. Okay. So P naught equal to 0. What about the coefficient of t to the power r minus 1 is then is lambda p1 plus r p naught, and p naught is 0. So P naught and P1 equal to 0, and then all the P's are 0. That is identical equal to 0. Okay. So with one differentiation you can find out this. If this is 0, implies this is 0. That's the point. Now what you do is you are differentiating r times to eliminate the particular term Pm that is coming there. Okay, or you differentiate it as many times as you want. Each time you differentiate it, you get a polynomial of the same degree with the property that if that is 0, then the previous term is 0. Okay, so you obtain successively through differentiations the coefficient Ri. After differentiating the terms so let me just write it in this way, that say you start with P, okay, differentiate it, call that P equal to P naught differentiated, you get P1, P2, P3 and so on, and eventually the last term is 0. So this term is 0 means the coefficient is here is 0, here is 0, etc., etc. So successively you can work out the details. I leave it to you to work out the details, because both these polynomials have the same degree, everything works well. Okay, right. All this, that e to the power lambda t is not equal to 0 is what matters. Okay, right. Therefore so this is the conclusion that you get. Therefore what you get, which implies what one gets is this, that is sigma I equal to 1 to am okay. Now, which in turn implies all the Cij's are that is independent and hence solutions equal to 0. This is what we are trying to find out. I mean, this is what we wanted to prove. Therefore, we have got a fundamental set of solutions. Okay, so that completes the proof. Now, having done this, I want to make some remarks. The remarks are, if you consider the inhomogeneous equation, then you know that the inhomogeneous equation of associated with L is of the form inhomogeneous or non-homogeneous equation associated with L equal to 0. Now, what is the solution of this? The solution of this equation is a solution of the homogeneous equation plus a particular solution of the inhomogeneous equation. So, somehow if you can find a particular solution of Lx plus Qt equal to 0, then if you already know the fundamental set of solutions for Lx equal to 0, then you can write the general solution of Lx plus Qt equal to 0 as a linear combination of the fundamental set of solutions plus the particular solution. This we have seen, and we have also seen two different methods through which you can actually find out this solution. What are they? One is the method of variation of parameters. The second method that we have used is constructing what you call a Green's function for L, so that you get a machine to generate the particular solutions of this once you know Q. Okay, so these are two things that we have done. So you can use the method of variation of parameters if you know a fundamental set of solutions for Lx equal to 0. I'll just for completeness, I'll just note it down. This is something which we have already seen very extensively. So recall that a a general solution of write down the non-homogeneous equation equal to 0 is the sum of a general solution of and this is exactly what we constructed here through the previous theorem, and a particular solution of the non-homogeneous equation of that is the non-homogeneous equation. Now we already explored some ways of finding out the particular solution. The particular solution may be obtained either by using the method of variation of parameters or by a Green's function for Lx. Now this we have extensively looked at. What we shall do now is to do an example so that we can implement this scheme and see how it works. So I can make some general remarks about the difficulties or the problems that you may encounter and so on. But we'll start with a physical problem. It's a very nice problem in mechanics that you come across. So we'll do some application. Okay, so we start with the following problem. So consider the second order equation. Second order et square plus 2k plus ft, where k and omega are by choosing omega square here we prefix that this is non-negative, okay, and k can take positive or negative values at the moment, okay. Now we interpret this equation. Now this is a second problem. Expressing Newton's law with 1 degree of that means only one dependent variable, where we attribute certain meanings for these terms. Omega square x represents a restoring force. I'll explain what it is towards x equal to 0, rather the position equal to 0, and this is proportional to the displacement I'll explain this after I write the whole thing. The second part, the second term that you have, I'm going to explain this one. For k is a damping force, proportional to the velocity okay, and the third term that is appearing there variable external So the physical scenario is this. This is the position x equal to 0. This is the x direction. Now you see, at any time, this is the position xt. So the particle is moving. Okay. So x is a function of t. Now what happens is this. See, you are writing an equation. What is this? The second derivative d2x by dt square is the acceleration of the particle at the time t. That is the rate of change of velocity. Velocity is given by dx by dt, position is given by x, and d2x by dt square is the acceleration that you talk about. So if you are taking a unit mass, then d2x by dt square is the rate of change of momentum. Momentum is the mass into velocity. Okay. So the term that you have here is the rate of change of momentum of a unit mass particle, and it's moving in some particular force system, and there are some built-in forces. The built-in forces are, one, of course, the so-called restoring force. The other one is what is called a damping force, and then you have an external force. So three things are happening there. So one is within the system itself. So what do you mean by restoring force? Restoring force is something like the force or the tension that you have on a spring. For instance, if you stretch the string and leave it, it will come back. Because what happens is, you see that the restoring force will start acting. Okay. So the farther away, there is more force which acts towards the point 0. So what happens is, when you look at the problem of simple harmonic motion, where what happens is, or even the pendulum swing, okay, it goes up, and then there is a place where its momentum is 0, then it starts receding back under gravity, and then go to the other end and go back, and so on, and it swings around. Now this is what you have in the system. Now if there are so there is something called a restoring force. That is what is called what is denoted by omega square x, which is proportional to the distance from the 0th position. The second force that is acting on it is dx by dt into 2k. This is where k is, if k is positive, then you see that this is going to be negative. So what you have is this minus 2k so x increases, this is a negative force. When dx by dt, the velocity increases, this is also a negative force whenever k is positive. This is what is called the damping force. Okay. So what happens is, you see, you have a sort of built-in resistance that works within, and this corresponds to that. And then you have an external force acting on the system. So what you have is the total force on the system is equal to the rate of change of momentum. Well, this is Newton's law. Okay. So this is how it comes. So this is the Newton's law that is working here. So the various forces acting on the system are separated now. One is the damping force, the other one is the one is the damping force, the other one is the restoring force, and the other one is the external force that is imposed on the system. So the equality of this will give you the what is called the Newton's equation to predict x at time t subject to some initial data. Okay, so that's a technical problem. That's a physical problem that you encounter. Now this leads to what is called a ordinary differential equation with the constant coefficients, which is linear, and therefore whatever we have done so far is applicable here, and we can make use of that and see what comes out. Okay, let us do that now. You can make some qualitative inferences from here. So when x increases, the pull towards x equal to 0 increases. Okay, and when it makes the momentum 0 there, when it matches with the momentum, then it becomes 0. So the particle is moving in this direction and there's a pull in this direction. And there's a place where the momentum is 0, then it starts reversing because of this force. It will be brought towards 0. So this is the problem that you have. So it goes to some extent where the momentum is 0 if you are ignoring this one. Then it comes back. Now suppose you have presence of this with k positive, then you see you have a damping force which is proportional to dx by dt. Of course, when x increases, normally what happens is the momentum, the dx by dt decreases. That is why, because of the restoring force, there is a decrease in dx by dt. Therefore the damping force decreases, but nevertheless, you know, initially itself it will not reach a place. So together they act, and then you see they balance the total force acting on that. And what happens is the particle will go to some place and it will come back, then out of momentum it will go to the other direction. Same thing happens here, and same thing happens here. What happens is it will be pulled towards 0 again. Okay, so this kind of, it will execute oscillation, but what happens is in the presence of a damping force, I am not assuming any external force. What happens is a particle will move here, go back here, so something like this. So this is 0. It will move here, then go back here, not as far as here, because what happens is the damping force will do the damage. And then what happens is it will go here, still a smaller length it goes, and then it will go a smaller length, smaller length, smaller length, and so on. Okay, so this is the sort of motion that executes along this line in the absence of an external force. If there is an external force, then of course this will get changed according to the nature of the force. So let us start working with Ft equal to 0. That is the homogeneous problem. That is no external force. Or 0 external force. Okay. Then we have the homogeneous equation. Plus 0. We are assuming k positive. Okay. Then what is this is a second order linear homogeneous equation with the constant coefficient. So the P lambda, that is the characteristic equation, is this is lambda square omega square, and the roots of this are lambda 1 equal to minus k plus square root of k square minus omega square, and lambda 2 equal to minus k minus omega square. All sorts of situations can arise, but we are assuming now omega is a real constant. Now if omega happens to be 0, then of course this will be, you will get minus k plus k and minus k minus k. So those scenarios we can look into separately, but what is interesting we will look into. Okay, then the general solution this, let me call, what did I write it? The first equation I called 1. Okay, so let me write, or I need this, right? 1 is, it's a homogeneous problem that we are looking at. Xt equal to C1 e to the power this is the general solution. So the problem essentially boils down to writing down the roots of the equation P lambda equal to 0. Then you can immediately write down the solution. Okay. So in general, when you deal with an nth order homogeneous linear equation, the difficulty is that the polynomial becomes a polynomial, a P lambda becomes, the characteristic polynomial becomes of degree n, and there is no specific way in which you can find out all the roots of this problem, even in C. So that's why you see the fundamental theorem of algebra becomes very relevant here, and although we do not know that how to get hold of these lambda i's, we still know that these lambda i's do exist. All the roots exist in C, and that's the power of that theorem. Okay, so we make the full power of that theorem to go further. Okay, so as far as mathematician is concerned, this kind of problems, that is the linear problem, is completely solved to the satisfaction. Although when it comes to the matter of application, it just crashes in many places, and the first place where it could crash is where you can, in the problem of, becomes a problem in algebra, whether you can find out the zeros of a polynomial or not. Okay, and as long as that problem remains open, no, it is not possible to solve this explicitly in all cases. Okay, now let us take a special scenario. We take k square omega square. This is a condition. Or I will make it more explicit. Now assume this is the assumption. Then lambda 1 and lambda 2 are non-real. Okay, because of the square root term that comes there, and we can write lambda 1 equal to minus k plus I beta, and lambda 2 equal to minus k minus I beta, where beta square is equal to k square. Okay. Now what happens? What are the corresponding solutions? As you said, this is a typical case where you come across what are called complex non-real roots of the characteristic equation, and you have what you call the complex valued solutions corresponding to these non-real roots. Okay, therefore the roots that you have are, so what are the solutions? The solutions that you have are, you see, you have a complex solution in fact, and you have already seen that if the coefficients are real, then the complex roots occur in pairs, conjugate pairs. That's what we see here. Okay. And the coefficients are real, the roots, the consequently, the corresponding solutions are conjugate to one another. And you see that you can work out the real solution. So what is this? So this is e to the power lambda 1 t equal to I so similarly e to the power lambda 2 t equal to e to the power minus kt, the complex conjugate of this, that is cos beta t, Now you can take the real and imaginary parts of this. So what you get? Hence, we obtain two linearly independent solutions which are linearly independent. The the other one will be just minus of that. So these are linearly independent. Of 1. So that forms a fundamental system of solutions. Okay. Therefore, now we can go to the next level. What is it? Yeah. Want to find out the solutions of the non-homogeneous equation. So how do we get a particular integral to the problem? So the general solution of the homogeneous equation is this is the general solution. Now we construct a particular of 2 by the method of variation of parameters. Now we allow C1 and C2 to be functions of t and then try to determine these functions, demanding that this satisfies the equation 2. Okay, so allow we set C1 derivative x1t equal to 0 and then y satisfies the non-homogeneous equation. Rather, you obtain those two equations by demanding that y is a solution of the non-homogeneous equation. Okay, right. Now solving, we can determine x1 prime and c1 prime and c2 prime. That is because you see that the Wronskian of not equal to 0. That we can easily verify. Therefore, this is equal to solving we obtain C1 derivative of t equal to minus the Wronskian x1 x2, which in turn is computes as 1 upon beta, verify this, e to the power kt into sine beta t similarly c2 prime t equal to okay, 1 upon beta therefore this is after simplification. When you expand this, you will get both terms, sine beta t and cos beta t terms will be coming there. Just verify this. This is, once you get C1 prime and C2 prime, you can integrate it. It's the integral of that and then put it back here and then simplify. This is what you get. So verify this. Okay. So the general solution of That gives the general solution where xt is given by this expression. Okay, right. So that's the method of variation of parameters. It also demonstrates several things in the process. Now what we want to do is we want to work on the Green's function. Once again, construct Green's function. For the homogeneous equation, for the equation or rather two, strictly speaking, you are inventing the inverse machine. Okay, this is a forward machine and you are inventing a backward machine. So that if you know x, then you can calculate f, and once f is given, you want to calculate the corresponding x. So you are actually inverting this. And this I have explained. Now you see, suppose s is something, then this is t less than 0, less than s, t greater than s. This is t. So let us calculate this. So we know that this is kst. Green's function is a function of both s and t, which is identically equal to 0, s, and kst is equal to e to the power minus kt. It's a general function where we have to compute c1 and c2. c1 cos beta t plus c2, which is essentially the linear combination. This is the general function that we have taken, and we have to determine c1 and c2. C1 and C2 are to be determined by allowing kst to be 0 at s equal to t and k to have a jump in the derivative at t equal to s. So let us work it out. So these are the conditions that we need. K zero and k derivative, that is derivative with respect to t, is what we indicate here. Minus 1. This is how we have defined the condition. Now computing C1 and C2, then xt equal to C1 equal to 1 by beta ks and C2 equal to minus 1 by beta e to the power ks cos beta s. Substituting, we get, so Green's function is even equal to 0, because that is what it turns out to be, because we get it continuous here because you are working on a second order equation. So we are insisting on the jump discontinuity only for the first derivative. So this is equal to minus 1 by beta e to the power k into t minus s this you verify and ensure that this is correct. Now suppose the initial condition for 2 is given by equal to 0. If you choose a different condition, it is going to be different. Then xt is given by minus integral t0 to t, you can work it out here, k yes. Now this is exactly, you can verify that this is exactly what we obtained for the with the variation of parameters also. Now we shall make some remark. Okay, so we have got the you go back to the construction of the Green's function and compute all these details. That will give you a lot of insight into the problem. So what is happening is this. In the Green's function, you see up to time t equal to s, everything is quiet. At that stage, there is a disturbance. And what is the consequence on the system for that disturbance? That's what we take. Okay. So now, suppose you consider the external force as a disturbance at various times. Yes. Okay. Then you have this as a, so this is actually the response of the system at time t for a unit force acting at s. Okay. So note that kst may be interpreted as the response at t for a unit disturbance at S. Okay. Therefore, now we assume, what we assume is that, so okay, so we'll take S. So let S1, S2, S3 be 3 points where unit disturbance then what is the solution? Then you can see that system being linear, KST, KS1T, KS2T, K are disturbances at are responses and the cumulative response KS3. Okay, therefore suppose F of disturbances of magnitude yes, then the response of such a distribution of disturbances external force is given by this. There are some actually from with the appropriate sign. The sign comes because you are using the discontinuity as -1. That is the reason. Okay. So the sign change is due to or I can write here. Okay. So I need not talk about sign change. So this is the response that you read. Okay. Now we want to make another remark. Another remark is about this Green's function. The Green's function is a for equations with constant coefficients that is something like KST, because if KST is a solution, then K, if X is a solution, this is because if XT is a solution, then so if you take T naught equal to S, then what happens? Consequently, K which is equal to sum H minus S, where is the response system at T for unit S. Now you also observe the following. The magnitude of, that is HST, is so HT goes to 0 as infinity, k is positive and ht goes to infinity as if this is negative. So the asymptotic behavior of h. Okay. Now you see that k is negative will bring in damping. Okay. Right. So it will, as I said, it goes there and then comes back, does not go to the extent to which it should have gone in the absence of that, and again, and it finally comes to an equilibrium. In the other case, what happens is it will start wildly oscillating. Okay, so I think with these remarks, let me stop. Thank you very much.